Varying the pitch of a propeller throws up two basic problems, one of blade actuation and one of pitch control. We will initially examine the problem of blade actuation. The issue of pitch control will be covered later in this lesson. Although mechanically or electrically actuated pitch change mechanisms are in use, the hydraulic method is the most commonly used. The system utilizes oil from the engine or reduction gearbox lubrication system as the source of hydraulic pressure. In this system, the pitch change mechanism is operated by a piston moving under the influence of the oil pressure. Use the up and down arrows on your keyboard to change the pitch of the blades on this propeller. Hydraulic pitch change mechanisms can be one of two types, single-acting or double-acting. A single-acting propeller has oil pressure applied to only one side of the piston. The return movement of the piston requires the force of a spring, or sometimes compressed gas. A double-acting propeller has oil pressure applied to either side of the piston, in order to move the propeller between the two extremes of fine and coarse pitch. Whichever type is used, the flow of oil to and from the actuating piston is controlled by a propeller governor. Dependent on the propeller manufacturer, the governor may also be known as a constant speed unit or propeller control unit. In addition to controlling the propeller pitch angle, the unit normally incorporates a small oil pump, which increases the oil pressure to the value required for system operation. A single-acting propeller is constructed basically like any other variable pitch propeller, in that the blades are arranged round a central, engine-driven hub with the cylindrical hydraulic pitch change mechanism mounted at the front. The pitch change cylinder, or dome, contains a movable piston which is activated by boosted engine oil pressure. Movement of the piston will rotate the propeller blades towards either coarse or fine pitch. Typically, rotation is accomplished by a mechanical linkage attached to the rear of the piston, which operates an actuating pin machined on the butt of each blade. The actuating pin is offset, in order that it can impart the correct range of angular motion. Generally, blade rotation towards coarse pitch is induced by an internal spring or gas pressure, and or counterweights attached to the blade roots. Most single-acting propellers, however, will utilize both a spring and counterweights. As we said earlier, some systems may use compressed gas instead of the spring. In feathering-type propellers, the spring has a dual function. It assists the counterweights in driving the propeller blades towards coarse pitch, and, when selected by the pilot, it actuates the blades into the feathered position, when engine RPM is low and there is insufficient centrifugal force acting on the counterweights. The constant speed unit, or CSU, incorporates a valve, which, because it has lands or grooves cut into the operating portion of its stem, is called a landed valve. This landed valve controls the flow of oil to and from the propeller actuating, or pitch change cylinder. A speeder spring, acting above the valve, tends to force the valve downwards, while a set of flyweights, driven by the engine, oppose the spring and act to lift the valve. An input from the pilot's RPM lever, or propeller condition lever, will adjust the setting of the speeder spring, selecting the RPM, which the CSU then automatically maintains. In order that it can respond to the various demands made by the pilot regarding the propeller RPM, the constant speed unit controls the oil flow to the pitch change cylinder in three ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed in the system, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will allow oil to drain back into the engine system as the piston is moved under the force of the spring, coarsening the blade pitch, causing an RPM decrease. One type of double-acting mechanism used on larger propellers, like the one shown here, achieves control of blade pitch angle by means of a hydraulically actuated piston connected to a cam slot, which rotates a bevel gear. The bevel gear engages with and drives other bevel gears located at the butt of each blade. Oil flow to either side of the piston is controlled by a propeller control unit. Alternatively, the type of control system shown here has a similar pitch change mechanism to the single-acting propeller. Like the single-acting propeller, its pitch change mechanism is also mounted towards the front of the hub, and the cylinder also contains a hydraulic piston. However, in the double-acting system, this piston will have hydraulic pressure directed to either side of it. Fine pitch oil is sent to one side of the piston, or coarse pitch oil is sent to the other. This eliminates the need for coarse pitch springs or gas pressure, and, with the exception of some larger propellers, the assistance of centrifugal counterweights. The double-acting propeller's controller will respond to the various demands made by the pilot regarding the propeller RPM to control the oil flow to either side of the piston in the pitch change cylinder in three ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, while simultaneously porting coarse oil to return. The piston will move to fine off the blades, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed which traps oil both sides of the piston, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will simultaneously allow coarse oil to be ported to one side of the piston and fine oil to drain back into the engine from the other side. The piston will move to coarsen the blade pitch, causing a decrease in RPM. A constant speed propeller must be capable of all the pitch change operations mentioned previously, as they are selected by the pilot moving the RPM lever in the cockpit. The system must also be capable of maintaining a selected RPM within its own operational limits, regardless of changes in airspeed, altitude, and engine power setting. When the constant speed unit senses that the RPM is as has been selected, the system remains in a static state. However, any change in airspeed, altitude, or engine power setting will result in a tendency to either increase RPM above or decrease RPM below the value selected. As we've seen already, a tendency for RPM to increase, an overspeed condition, will be countered by a supply of oil being fed to the coarse pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then coarsen and propeller torque will rise as a result of the increase in the blade angle of attack. Propeller torque now exceeds the engine torque and will cause the RPM to decrease back to the selected setting. As the RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the position in the pitch change mechanism immovable, until the next RPM selection or disturbance in airspeed, altitude, or engine power setting. A tendency for the RPM to reduce, which is termed a propeller underspeed condition, must be countered by a supply of oil being fed to the fine pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then fine off, and propeller torque will fall as a result of the decrease in the blade angle of attack. Propeller torque is now less than the engine torque, and will cause RPM to increase back to the selected setting. As RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the piston immovable until the next RPM selection or disturbance in airspeed, altitude, or engine power setting.